Welcome back, everybody. This is our first session in JEE Mains previous year questions for chapter Electromagnetic Induction of class 12th. Before this video, we have made similar videos for previous chapter. Till now, we have covered for class 11th complete and 5 chapters of class 12th. So all of those related videos for JEE Mains previous year questions are available on the channel's playlist section. You can find all of them in the playlist. We have also started similar series for neet previous years, so and all of those videos also available in their dedicated playlist in the channel's playlist section. And if you find these videos useful, then do press the like button, share them, and subscribe to our channel. Also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. With this, let's start today's video. And here is the first question. Two concentric coils C1 and C2 are placed in a XY plane. C1 has 500 turns of radius 1 centimeter and C2 has 200 turns and radius 20 centimeter. C2 carries time dependent current that is given by this equation, the EMF induced in the C1. So let's slide it down. That's one side and draw the diagram. So basically we have two coils. Suppose this is our first coil and this is our second coil. Both are concentric. Now C1 has 1 centimeter. So this is C1. Smaller ring is C1 and bigger ring is C2. And C2 has a current. Means if C2 has a current, then magnetic field will be produced by the C2. And flux, that EMF which we have to calculate, that is we have to calculate EMF produced in the C1. Means we will calculate the amount of flux that is related to, or the amount of flux linked with coil C1, and then we will calculate its rate of change to find out the value of EMF. So we have to calculate phi C1 EMF, flux associated with the coil C1, and we know that flux is magnetic field into area, and here magnetic field will be produced by the C2. So magnetic field due to C2 into area of C1. So that will be the equation, magnetic field due to C2 and area of C1. Now radius of C2 is 200 centimeter and radius of C1 is 1 centimeter. So basically we only have formula for center of a coil, magnetic field at the center of the coil and not at any point inside, not at any random point inside in the coil. So we will assume here that C1 is the magnetic field in the whole area of the C1. Magnetic field in this whole area of C1 is same as that of the center of the C1. So that is our assumption here. So magnetic field value will be, so our equation will become phi flux associated with C1 will be magnetic field due to C2 at the center, that will be number of turns in the C2. So suppose those are N2 into mu node into current it through it divided by the radius of C2 multiplied by pi r C1 square. So now this is the value of the flux associated with the ring C1. Now we have to find the induced EMF, and induced EMF is given by minus of d phi by dt, and in this expression of the flux only I is variable, else or all other values are constant. So it will be N2 mu node pi rc1 square by twice rc2 into, with negative sign, of di by dt, and the value of I is 5t square minus 2t plus 3, and from this di by dt will be 10t minus 2. So substituting this here, we will get minus n2 mu naught pi rc1 square divided by twice of rc2 multiply 10t minus 2. Now we have to find EMF induced at t is equal to 1. So EMF induced at t is equal to 1 will be, now we will substitute all the values, and also here it is area. This is the area of one coil, and C2 also has 200 tons, so N1 will also come here. So we will have N1 N2, N1 N2. So minus value of N1 is 200. Sorry, yes. Value of N1 is 500 and N2 is 200. So 500 into 200 into mu naught, that is 4 pi into 10 raised to power minus 7 into pi into rc1 square. So radius of the smaller coil, that is 1 centimeter or 10 raised to power minus 2. Squaring it, we will get 10 raised to power minus 4 divided by twice of rc2, that is 20 centimeter or 20 into 10 raised to power minus 2. Multiply by, we will substitute t is equal to 1 here, so 10 into 1, 10 minus 2, that will be 8. So now we can solve it. This will be go on 4, this 4 over 2, and we will have 10 here. Now minus as it is 5 into 2, 10 with 4 zeros, so it will be 10 raised to power 5 into 4 pi square into 2. So let's write it like this: 4 pi square multiply 4 pi square into 10 raised to power minus 7 minus 4, so minus 11, multiply by 2 divided by 10 raised to power minus 1. So it will be 4 into 2, 8 into pi square is almost 10. Now this is negative sign as it is. 10 raised to power plus 5 into minus 11, so 10 raised to power minus 6, and this minus 1 will come in the top, so to become 10 raised to power 1. So this will become minus 8 into 10 raised to power minus 4, and we can write it like negative 0.8 millivolt, and it can be further written as minus 4 by 5 millivolts. And if we go here, so EMF induced in millivolt is written as 4 by x, and what we obtained here, we obtained as minus 4 by 5 millivolt, ignoring the minus sign because it is only represented as 4 by x. So our value of x will be 5 here. Let's move to the next question. So a small bar magnet is moved through the coil at constant speed from the one end to the other. Which of the following series of observation will be seen on the galvanometer G attached to the coil? First represents magnet's entry and second represents when a magnet is inside the coil, and third represents the magnet exit. Now let's slide it down slightly. We know that EMF is induced when there is change in the flux linked with some coil or some closed circuit, and this flux is filled into area. So in this case, we know that as magnet is moving, so let me draw here. So with the help of diagram, suppose this is our this coil. This is our coil, and we have a magnet here. Now, when this magnet is moving towards the coil, then area of the coil is not changing. Area of the coil is constant here. So only the value of magnetic field is variable, and as magnet comes near this coil, value of magnetic field is increasing. So if value of magnetic field is increasing, means we are having some variation here, or we are getting some change in flux. And if there is change in flux with respect to time, then there will be EMF induced. Means when this magnet is just about to enter into this solenoid or coil, there will be some current flowing in the galvanometer. We are not sure about the direction of the galvanometer's deflection, but there will be deflection when this magnet is just about to enter. Then there should be some deflection in the galvanometer, and as we see from the options, in the option A there is no deflection. It is in the initial condition, so A get cancelled. Option A get cancelled. Similarly, option C gets cancelled. That in option C also there is no deflection. Now coming to the second part, that when magnet is completely inside. So now when this magnet is completely inside, what is happening? As always, area is already constant, and the amount of magnetic field associated with this solenoid, or amount of magnetic field associated with the coils of the solenoid, is not changing. How it is not changing? Suppose let us mark some numbers on these rings. This is ring A, ring B, ring C, and ring D, and ring E. Now when this magnet is approaching towards the ring A, so amount of magnetic field linked with ring A is increasing. So amount of flux increase linked with ring A is increasing. So we are getting some EMF induced. Now when it crosses ring A and reaches to ring B, now amount of flux associated with the ring B is increasing, but on the same time amount of flux associated with the ring A, because now magnet is going away from the ring A, so amount of magnetic field linked with the ring A is decreasing. So increase in magnetic flux with ring A is balanced by the decrease in the flux with the ring B. So individually there will be increase in the flux for ring B, or we can say as an individual for the ring B there is some magnetic field some flux, some EMF induced. But on the contrary, with the ring A, where magnetic flux is decreasing, opposite potential will be produced. So suppose we can say in the ring B there is, let's say, suppose plus 5 voltage is produced, then in the ring A negative 5 will be produced, and as a whole they both will cancel each other, and this keep on happening until this magnet is keep on moving inside the solenoid, because as it start moving toward one of the coil, then it is also moving away from the another coil. So their mutual flux changes cancel each other. So as a whole, when this magnet is inside the coil, there is no change, there is no net change in the flux. And if there is no net change in the flux, means when magnet is inside the coil, the galvanometer will not show any deflection. And that we find in option B, that in second case there is no deflection, and in option D, in second case there is deflection. So option D gets rejected, and option B is the right answer here. So with this, let's move to the next question. Here, an elliptical loop having resistance R of semi-major axis A and semi-minor axis B placed inside a magnetic field as shown in the figure. If the loop is rotated about x-axis, so loop is rotated about x-axis with angular frequency omega, the average power loss in the loop due to joule heating will be. So we have to find out average power loss, and that due to joule heating, and we know that amount of heat lost due to joule heating is given by heat is equal to I square R into T. That is the amount of heat lost. Now to get up to this formula, what we need to first find out the amount of induced EMF, and then we can calculate the amount of current flowing in the circuit. And we know that amount of induced EMF is given by negative of d phi by dt, which will be negative of d by dt of magnetic field into area. As magnetic field is constant here, and as we rotating this loop, so area is changing here. And as area is changing, so we have to represent area in the terms of, we can say, as it is rotating with angular frequency omega, so we have to represent area in terms of angular frequency omega. So for that, to represent area in terms of this angular frequency omega, we can write area in two ways. So area can be either written as A cos omega t, because omega into t is theta, or we can say A is equal to A sine omega t. We can use any of these depending upon the situation we have. So let us consider this is the initial condition. In this initial condition, as given here, the areal vector is always perpendicular to the plane of the area. So initially, area vector should be like this. So we can say initially the angle between area vector and the magnetic field is 0, and we have we can say the multiplication of magnetic field and area will be maximum, as this is dot product of magnetic field and area, and initially they have the same direction, so their dot product should be maximum. So for that, if we have to keep dot product maximum at theta is equal to 0, then we have to use the cos, because if we put a cos into omega at t is equal to 0 initial condition, this will give us area will be equal to, suppose this is a node, so area will be equal to the a node or the maximum possible area. So here area will be used here as a cos omega t. So let's find out the flux. So flux will be phi minus d by dt p a cos omega t. This will give us minus b a omega, derivative of cos is negative sign, so negative negative positive sine omega t. So not phi, this is E induced EMF. So value of induced EMF is this, and then value of current will be induced EMF by resistance, so it will be B A omega sine omega t divided by resistance R. So that's the value of the current. Now we have to find out average power loss. So average power will be P average, that is either E square by R or I square into r, we can use whatever we want. So we are using E square by r, so it will be b square a square omega square sine square omega t divided by r. As we have to find average, means we have to take average value of all of these. Here magnetic field is constant, this A is constant, area is not constant, this A is constant, area is changing with the using this expression A node cos omega t, and variable area is represented by sine term here. Omega is constant, r is constant. The only thing that is variable, that is omega, or sorry, we can say t. The time is changing, due to which omega t is variable, and this omega t is variable, this is changing the value of sine. So we can say our answer will be b square a square omega square divided by r into average value of sine square omega t, because this term is keep on changing with respect to time. All other terms are constant. Now average value of if we have to find average value of sine omega t, that is 1 by root 2, and average value of sine omega t, that is 1 by 2. Average value of sine omega t is 1 by root 2, and average value of sine square omega t, that will be square of that is half. So our average power loss comes out to be b square a square omega square by twice of r. Now area, the value of area we can put, as this is a elliptical shape, so area will be pi times a into b. So it will be putting value for area, that will be pi square a square b square into capital B for magnetic field into omega square divided by twice of r. So option A will be the right answer here. Now let's move to the next question. A uniform magnetic field B exists in the direction perpendicular to plane of square loop made of a metal wire. So there is uniform field. The wire has a diameter of 4 mm and total length of 30 centimeter. The magnetic field changes with time at a steady rate. Okay, so initially it is mentioned that field is uniform, then it is mentioned it is changing. So field is variable. Now induced current in the loop is close to. So we have to find the induced current, and to find the induced current, first we need to calculate the rate of flux change. From that we will calculate the induced EMF, and then we divide induced EMF by the resistance, and from that we can calculate the current. So let's first find out the induced EMF. So induced EMF will be, ignoring negative sign here, it will be d phi by dt, and as area is constant, field is changing, so it will be a dB by dt. This is induced EMF, and current will be E by R, so A by R dB by dt, and we don't have direct value of resistance here. In short, we have been given resistivity and diameter and the length of the wire. So we can write it like rho area as it is, rho into L into area of cross section. These two areas are different here. This is the area of the loop, and this is the area of the cross section of the wire into dB by dt. So we can write it like further. Now area of the loop, as this is a square loop of side length 30 centimeter. So area of the loop will be 30 into 10 raised to power minus 2 into 30 into 10 raised to power minus 2. Wait a minute. Total length is 40 centimeter, 30 centimeter. Actually length is not. So we have to correct this. Means this is our loop and its total length is 30 centimeter. So Suppose if side length is A, then 4A is equal to 30 and A is equal to 15 by 2 centimeters. So that's the side length, and that will be used to calculate the area. So it will be 15 by 2 into 10 raised to power minus 2 into 15 by 2 into 10 raised to power minus 2. This is the area of the loop. Now area of the cross section of the wire, that will be pi into radius square. As diameter is 4 mm, so radius is 2 mm. So 2 into 10 raised to power minus 3 into 2 into 10 raised to power minus 3. That's the radius. Now divided by the resistivity. Resistivity is 1.23 into 10 raised to power minus 8 into length. Now this length is the length of the wire which is used to find the resistance of the wire. This length is the length of the wire which is used to find the resistance of the wire, and to find the resistance of the wire we will use its complete length. So that is 30 centimeter. Assume we have a wire which has a length of 30 centimeter. So to calculate its resistance, we will use its length as equal to 30 centimeter. So this will be 30 into 10 raised to power minus 2, and into, now we are left with dB by dt, that is given to be 0.032, or we can say 3.2 into 10 raised to power minus 2. So that will be the whole expression. Now this 2 and this 2 get cancelled with this, and you can say 15 cuts this 30 on 2, and this 2 divides it, no, 1.6. So we are left with 15 into 10 raised to power minus 4 into pi into 10 raised to power minus 6 into 1.6 into 10 raised to power minus 2 divided by 1.8 into 10 raised to power minus 10. Now 10 raised to power minus 4 minus 6 minus 10, so minus 10 get cancelled, and we are left with 15 into 1.6 into pi into 10 raised to power minus 2 divided by 1.23. And solving this, we will get 61.27 into 10 raised to power minus 2, and it can be written as 0.6127 ampere. So that is our option B as a right answer. So let's move to the next one. A circle coil of radius 10 centimeter is placed in uniform magnetic field. So magnetic field is uniform in its plane perpendicular to the field. So initially its plane is perpendicular to the field, or we can say, suppose this is our coil, and suppose this is the direction of the magnetic field. So plane of this coil is perpendicular to magnetic field, or we can say its area vector is in the same direction as of magnetic field. So here initially, if this coil is rotating, as it is already mentioned that coil will rotate, so we have to use area is equal to A node cos omega t, because in the initial condition t is equal to 0, area is maximum in the direction of the field. So we will use cos component here, not the sine one. So it is rotated with constant angular speed about an axis with diameter of the coil and perpendicular to magnetic field, so that it undergoes half of rotation in 0.2 second. So half rotation in 0.2 second, or we can say full rotation in 0.4 second, or time period is 0.4 second. From that, we know that omega is 2 pi by t. So that will be 2 pi by 4 into 10. So it will be 2 and 5. So omega is 5 pi radian. The maximum induced EMF in the coil will be close to. So we have to find maximum induced EMF, and we know that induced EMF is minus d phi by dt. Here field is constant, so it will be minus b into dA by dt, and it will be minus b into d by a dt of a node cos of omega, that is 5 pi into t. So it will be further written as minus b a node 5 pi. Derivative of cos is negative sign, so this will be positive. So it will be sine 5 pi t, or we can write as that value, maximum value of induced EMF will be when this whole expression is maximum, and here b is constant, a node is constant, 5 pi is constant, only variable is 5 sine 5 pi t, and this will be maximum when t is equal to, we can say, value of t such that this whole 5t reduces to pi by 2. We can also find the value of time. It will be maximum when 5 pi t is equal to pi by 2, because sine pi by 2 is equal to 1. So from this, time is equal to 2 by 5 seconds. And maximum value of this sine expression will be 1, and we, as we have to only find the value maximum EMF, so we assume this is equal to 1. So maximum EMF comes out to be b a node into 5 of pi. So value of magnetic field is 3 into 10 raised to power minus 5. Area, as it is circular coil, so it will be pi r square. So pi times r, that is 10 centimeter. So 10 raised to power minus 1 meter, squaring it 10 raised to power minus 2 into 5 into pi. Now pi into pi is almost 10, so pi square is 10. Now 3 into 5, 15. So we will get 15 into 10 into 10 raised to power minus 7, and that is 15 into 10 raised to power minus 6, and it is can be written as 15 microvolts. So that will be our answer, and it has to be represented in microvolts, so 15 will come here. So with this, I end this video here. Again, if you find this video useful, helpful, then do press the like button, share it as much as possible, and subscribe to our channel. If you have any doubts or suggestions, put them in comment section. I will try to resolve them. Also, if you like to donate us something, then you can scan any of these QR codes in front of your screen and donate us with whatever amount. Any amount of even a small amount will be highly appreciated. With this, again, thanks for watching, and we will meet in next video.